What is up, guys? Welcome to another episode of CCT. Today we are going to be going over the lowest common ancestor of a binary tree problem. I think it's best to explain by drawing it out quickly. Obviously, if you already know it, feel free to fast forward. Okay, hold up. So, if we have a tree, also, it's worth noting all of these are unique. Does it have to be a binary? No, it's not like a ordered binary tree. Let's just get some things out. 7, 10, 3. Okay. So what it is given two nodes, like let's say 2 and 13, and the root here, what you want to do is figure out where these two nodes meet, or would intercept paths first, which in this case would be 4. So the answer here, you would return this node here. Okay, so my first thought is, I kind of said it in this way, finding where the paths intercept. So my first thought was like, okay, what if I could find the path 1, 4, 2, and then, like, by traversing the whole tree, obviously, and then, like, eventually get a vector of those values, or I guess actually the tree nodes, because you want to return the tree node. And then 1, 4, 8, 13, and then just see where they start to diverge, and then these would be your lowest common ancestor. And that works. It does work. However, there is a much more complicated, much more efficient recursive way to do it. Because here you have to go through the tree twice. I think, yeah, I'm not sure if you can do it all in one go. Yeah, so I'm going to say 2n time complexity at least, and then like plus maybe some n to like find the intersection, whatever. But it is at the end of the day, O of n. But there is a space complexity. So mem is like, I don't know, probably also like, well, yeah, you have to think of like worst case scenarios. So we could do it recursively without this stuff. And how you do it is you have to think about, okay, so you have these two nodes that you want to find the intersection of the path. So first thing you got to do is you got to get to the node. So somehow do some kind of depth first search to get to, maybe it gets to this 2 first. Okay, fine. And once you find that 2, like, I'm trying to walk through it as if I don't know the solution. So you find the 2, and then you like bump back up to here, and then you find the 13 here. Okay, how do you know that 4 is the ancestor? Well, one idea you could have is if you can do something on the left and get one of the nodes you're looking for, and do something on the right and also get one of the nodes you're looking for. So you get something from this side and from this side. That guarantees that you're the ancestor. I mean, let's think about it. Even if you go back more, like maybe you think, oh, this also looks like it could be the LCA. Or by that logic, could be the LCA, lowest common ancestor. Well, it can't, because it could find one of them, or in this case both of them, using its left path, but it can't find anything on its other side. So the lowest common ancestor, so here, this is our key observation. The lowest common ancestor can find one of the elements on its left side and finds one of them on the right side. So how about we do something on the left, do something on the right, and we store a tree node for the left side and the right side. And the left side's going to get something, doesn't even have to be the two, but it's going to get something if it found the node, and it's going to get nothing if it didn't. And then we could say, like, by the time that it gets up here, it gets something from the right subtree, or left subtree, gets something from the right subtree. Classic recursion, right, in a binary tree. We'll do something on the left, do something on the right. And if it gets something from both of these sides, aka not null from both sides, then we can just return this. Let's get some pseudocode going. Yeah, we have enough space here. Let's choose this color. Okay, so let's say tree node pointer. This is how I always like to start recursion. Start with the main part of it, what you're doing on the left and right side, and then maybe the edge cases, and then other stuff. So tree node left gets, let's call this, the function is foo, and foo takes in the root, p, and q, all of which are tree nodes. So what we could do is call foo on the root left with p and q. Remember, these are the things that we're searching for. And then we could do tree node right gets foo right p and q. And so something we could say right now is if, so this is a shortcut for not null. Wait, no it's not. Wait, sorry. This is a shortcut for not null. So if the left side is not null, because if it's null, then this evaluates to false. So if it's not null, then it evaluates to true. So if left is not null and right is not null, we can return the root. All right, hopefully this part of the logic makes sense. So we somehow return the actual element or something if it finds either p or q on the left side. And if it doesn't find it on the left side, then the left should hopefully get null. And then it does the same thing on the right side. It searches for either p or q, and if it finds it, it'll return, I don't know. It really doesn't matter, because all we're checking for is that it didn't return null. So if it finds it, just make sure you don't return null. I don't even care what you return. But if you don't find it, return null. Okay, fair enough. So then to get these base cases right, for like when do we stop here? I think it's fair to say, can I move this? Wait, now I want to move it, sorry. Cut, and then paste? No. Oh, I can't do that. Oh, wait, hold up. I'll try that later. I probably didn't need to cut that, actually, now that I'm thinking about it. Yeah. That's good. Okay. So I think it's fair to say that if we've gotten to where the root equals p, then like if we get to the root equals 2 or something, then we could just return p and or root. I mean, they're the same thing, right? If root gets to the q, let's just return q. All right, so this is saying if we get to them, then if the root gets to one of the ones we're searching for, then return that. If it gets to null, so if you end up with null, so if, okay, I'll do a shortcut. So this is if it equals null, then just return null. Okay. Let's trace through what we have here. Could I zoom out a bit? Whoops. Yeah. Okay. Let's go back to purple. So, okay, so we start off here. This is not P, this is not Q, this is not null. Next thing we do is we go to the left side. We're at this one, and it goes back up here. Is this P? No. Is this Q? No. Is this null? No. Next line, go left. Okay, got it. So I'm here now. Is this P? Sure. Yeah, we'll like 13. 1. This is what we put in here. So yes, it is P. So we are returning 2. Okay, so that means left just got 2. So left got 2. And now we're back at the iteration where 4 is the root, right? Because when 2 is the root, just returned here, and now left equals 2, or the tree node that points to 2. Our root is still 4, and we are about to go to this line. So go right. So now we're here. Does 8 equal P? No. Does 8 equal Q? No. Null? No. This line, go left. Okay, so now we're here. We're at 3. Does 3 equal P? No. Does 3 equal Q? No. Does 3 equal null? No. Go left. Okay, so that's like here. So this is null. Null. So then it gets to here, and it does equal null, so it returns null. Okay, so that was 3's left side. Then 3 goes into the right side, and now the root is null again, and then it returns null. So we should probably add here if you get to a point where they both equal null, what do you think you should do? You should return null. Because 3 came up empty-handed, and our whole idea is if you come up empty-handed, meaning you haven't found the 2 nodes you're looking for, just return null. Okay, so this was 3's iteration. 3 just returned null. That means when we're on 8 as the root, this left side just got null. It didn't get 3, it got null. Right side, 8 goes on to 13. Now that we're at 13, does it equal P? No. Does it equal Q? Yes. So this gets returned here. And so let me just write that. That was null. And now the right side gets 13. And this is when 8 is the root. Okay, interesting. Seems like we're at a case that we haven't had before. So does left and right both equal something? No. Does left and right both equal null? No. One of the sides equals 13. One of them equals null. What should we do? Well, what we could say is that 8, this root, is not the LCA. But we should probably like return something so that the future LCA as it gets popped up or whatever knows that it found one of the P and Q further down here. So what I'm going to say is that if one of them is null and the other one is something, let's return that something so that when that something gets to the real LCA, that LCA can have something from the right and something from the left. So, in other words, okay, hold up. We could use some complementary logic. So else if, so we know they're both not. So if left, then return left. I should totally zoom in. So else return right. This is just using some complementary logic. So we know that they're both not something. We know that they're both not null. So that means if one of them is something, then the other one's null, and we could just return the something. Feel free to pause and check my logic there. I'm pretty sure it's right. Okay, so now 8 just returned. So when the root was 8, it just returned 13. So that means pop back to this iteration where 4 is the root. The left side has 2, and the right side, oh, it does have 13. Huh. Okay, it has both. What should we do? We return the root. Okay, so 4 has been returned, so 4 gets popped back up here. And then we get to this iteration where 1 is the root, the left side is 4, and we haven't gone here. But I can tell you right now that at the end of this, when it goes to the right side, it'll get null because nothing is here. So, according to our logic, this is convenient because when one side is null and the other side is a number, we just return the one that's a number. So 4 in the end is returned. Okay. Yeah, I just want to make sure that you guys don't think that was just like a coincidence that like 4 was just returned when this side was null. You could think of it as like if 1 had something returned from the left side and nothing returned from the right side. But by the way, we are assuming that P and Q are in the tree. We are assuming that. So if you get to the point where you're at 1 and one side has something and the other hasn't, it means 2 things. 1, either the thing that just got returned is the root, which in this case it is, or 2, the thing that just got returned is either P or Q, in which case the tree would have to like expand up here such that it eventually finds Q on the other side or P on the other side. So yeah, that's a bit of a tricky case to think of, but it does work out. So just to highlight again, key observation that you have to make is that you're the LCA if your left side and right side both have something. If they both have nothing, then then we should just return null. And when one of them has something and the other one doesn't, we should return the thing that has something, so that here's the 2 options. So that either if you are P or Q, you will eventually pop back to the LCA, or in this case, when we returned 4 over null, because 4 is the actual root, and we want to just return it. We want to pop it back up to the first iteration and just return it. Okay, so since this is the code and I know it works, maybe there's an error somewhere, but the logic is pretty solid here. I'm not going to type it out. Well, actually, I did already type it out. Why does this look green? What the heck? Is this just my eyes or something? Alright, anyway, this is the code here. This one runs and it gets you a decent score here, like faster than 81%. Well, I hope you learned something and saw something or learned something as I went through my thought process. This was one that I obviously already looked at the answers for, and yeah, so I hope you enjoyed. I'll see you next time.